This lecture is going to go over some of the pre-lab material needed for experiment 6, dealing with calorimetry and heat calculations. We have three objectives with this lab. The first is to investigate the first law of thermodynamics. The second will be to identify an unknown metal by finding its heat capacity. And finally, to determine the heat of neutralization from the reaction of HCl and sodium hydroxide. So first, a little bit background and a little bit on the first law of thermodynamics. This law states that the energy of the universe is constant. We can see this written in a few different ways. One of the ways we see this is by this equation here, where delta E, the change in energy, is equal to heat Q plus work W. So the change in energy of a system is equal to the sum of all of the heat and work transferred in that system. Now, when we think about changes of heat and heat flow, one thing to keep in mind is direction and watching your sign. Anytime energy is negative, whether that's a delta E value or a Q value for heat, if Q is negative, that means heat is being lost. So negative means something is flowing out. In this case, it would be an exothermic reaction. If Q is greater than 0, that means energy is flowing in, and this is an endothermic chemical reaction. All right. So we're going to be doing calorimetry for this lab, and this is the science of measuring heat. A calorimeter is an experimental device used to determine the heat associated with a chemical reaction. There's many different types of calorimeter. One of the very common ones is what's known as a coffee cup calorimeter. And this is nothing more than a couple of stacked insulated styrofoam mugs. You can imagine we want something well insulated, so any heat that's transferred stays inside the calorimeter and doesn't get lost to the surroundings at large. So when we're dealing with calorimetry, we're measuring heat, and one of the things to keep in mind is that heat Q at constant pressure, so Q sub P, is equal to delta H. So it's equal to the change in enthalpy of your system. That's a really important piece for us to recognize. That also means that if we can measure the change in temperature going on inside of our calorimeter, we're going to be able to relate that to what delta H is and what Q is. All right. So within calorimetry, remember the first law of thermodynamics says energy is conserved. So we can have a heat flow from one thing to something else, but that all has to be accounted for. So we can see the heat of the system, oftentimes we think of that as the chemical reaction, has to go somewhere, and oftentimes it will go to the surroundings, which we usually think about as being the solution that the reaction takes place in. So in this case, we could have a chemical reaction taking place in our coffee cup calorimeter, and the surroundings would be the aqueous water environment that the reaction takes place in. We're going to be measuring the temperature change, and how much change in temperature there is depends on a few things. It depends on the enthalpy, and it depends on the identity and the amount of the surroundings. Is this reaction taking place in water? Is it in 5 grams of water or 100 grams of water? Is it in a different substance? All of these things will have an effect on what the ultimate delta T of the reaction is. So we can summarize that in an equation shown here, where the heat gained or lost by the surroundings is then related to the specific heat of a substance, capital C, the amount of the substance, M, usually that's in grams, but it can be in moles, we have to watch our units, and the change in temperature, delta T, which is always final temperature minus the initial temperature. So a little bit more about C, the specific heat. When we think about the specific heat, we can actually look up the specific heat of substances in tables. And the specific heat is defined as the energy required to raise the temperature of 1 gram of the pure substance by 1 degree Celsius at constant pressure. And we can see for water, the specific heat is 4.18 joules per gram per degree Celsius. We can look up a bunch of other elements on this table as well, and for the second part of the lab you'll have to determine what the specific heat is for an unknown metal and look it up on a table like this to confirm its identity. So going back to our calorimetry slide, we can put this all together in our equation where the heat absorbed or lost by a substance is equal to the heat capacity times the amount of the substance times the change in temperature of the substance. Okay, so a little bit more about this lab. This lab will be completely remote. We're going to be using the online calorimetry simulator with a link shown here. It's also in your lab material. It'll have 3 parts. The first will investigate the first law of thermodynamics by mixing hot and cold water, and then we are going to calculate the amount of heat lost by the hot water and the amount of heat gained by the cold water. In part 2, we are going to identify an unknown metal. We will heat a hot metal in water and then place that into a different beaker of water and measure the amount of heat absorbed by the water and use that to determine the specific heat of the metal. And then finally, we'll have to determine the heat of neutralization of the mixture of reaction of a strong acid and a strong base. So first, part 1. In our calorimeter and in our simulator for this one, we're going to mix known amounts of hot water and cold water, where we know the initial temperature of both the hot and cold water and the mass of the hot and cold water. If we mix these in a calorimeter, according to the first law of thermodynamics, energy is a constant, so that means that the total energy change has to be 0, and that's also going to be equal to the heat. 0 has to be equal to the heat flow from the hot water and the heat flow from the cold water, and so we can see that the heat lost by the hot water has to be equal to the heat gained by the cold water. It's the same in magnitude. One of them is negative because the heat is flowing in opposite directions. It's going from hot to cold. Now, that's the heat flow. We can substitute out Q and instead call this negative MC delta T for the hot is equal to positive MC delta T for the cold. And here we can see, in this case we'd be solving that we have the same thing on both sides of our equation. Next, we can identify, in part 2, we're going to identify an unknown metal. The way we'll do this is by taking a small piece of a metal, taking its mass, putting it in boiling water so we can heat it to exactly 100 degrees Celsius. And then you can imagine dropping that hot piece of metal into a calorimeter with a known mass of water. We can then monitor the temperature change of that water, and again, according to the thermodynamics first law, we see all the heat lost from the metal has to go into the surroundings, the water, and so the heat flow are equal. And so again, we can now see that so in the first investigation, we're going to look at the first law of thermodynamics. And what we're going to do is we're going to mix known amounts of hot water and cold water in a calorimeter. And according to the first law of thermodynamics, we know that the total energy change has to be 0. So we can write that out as delta E equals 0. That also means that has to be equal to the sum of the heat flow from the hot water to the cold water. We can rearrange that equation and say negative Q of the hot water has to be equal to Q of the cold water. So all the heat lost by the hot water has to be equal to all the heat gained by the cold water. We can then substitute in for Q and say that negative MC delta T for the hot water has to equal MC delta T for the cold water. And so we'll see how that works in this first part of the experiment. In the second part of the experiment, we're going to identify an unknown metal. And here what we can imagine doing is taking a small amount of unknown metal, placing it in boiling water to heat it to 100 degrees Celsius. And then you can imagine taking that hot piece of metal and transferring it into a calorimeter with full of water with a known mass. Here, all of the heat lost by that metal has to go into the water in the calorimeter. And so again, we can use that first law of thermodynamics to say the heat lost by the metal has to equal the heat gained by the water. So now when we look at this, we can say negative mc delta T for the metal is equal to mc delta T of the water. And when you consider this equation, our only unknown we should have is the C of the metal, the specific heat of the metal. Once we have that from our calculations, we can look it up on a table. In our third part of our lab today, we're going to be looking at a heat of neutralization, and we're going to be trying to determine the enthalpy change for a reaction. And a couple things to note is delta H, the enthalpy change of a reaction, is equal to the transfer of heat into or out of the system when we're performing this reaction at constant pressure, which we will be for this lab. Typically, when we think about enthalpies of reaction, we'll report these on a per mole basis, and so we're going to have to adjust for that in our final calculation. So what we're going to do is inside our calorimeter, we're going to combine hydrochloric acid and sodium hydroxide of a known molarity and a known volume. And then we will measure the temperature change that takes place from this chemical reaction. And in this case, the heat gained or lost by the chemical reactions has to be equal to the heat gained or lost by the surroundings. So we're actually measuring the temperature change of the surroundings, which is the total amount of water that's present. And where did that heat come from? It had to come from the chemical reaction. So the heat lost by the chemical reactions goes into the surroundings. And so once we know what the heat of reaction is, Q of reaction, we can divide that by the number of moles of either a product formed or a reactant that's reacted to determine delta H of reaction in kilojoules per mole. Thank you.